Good afternoon, everyone. Today I am excited to share insights into our research titled Distributed Multi-Intersection Traffic Flow Prediction Using Deep Learning. My name is Idriss Moumen, with my colleagues Rabie, Mahdaoui, Fatima, Zahra, Raji, and my supervisors, Professors Najat, Rafalia, and Jaafar Abouchabaka. We are from Department of Computer Science at Faculty of Sciences, Ibn Tufayl University in Kenitra, Morocco. This research explores innovative solutions at the intersection of urban mobility and artificial intelligence, aiming to revolutionize how we perceive and manage urban traffic dynamics. We will delve into a novel approach that harnesses the power of deep learning, specifically the gated recurrent unit architecture, to predict traffic flows across multiple intersections simultaneously. Through this presentation, we will uncover how this model not only enhances prediction accuracy, but also plays a crucial role in advancing energy efficiency and sustainable urban development. Urban areas face a pervasive challenge, traffic flow, traffic congestion. This issue permeates various aspects of daily life, causing inefficiencies, increased travel times, and environmental concerns. The ramifications extend beyond inconvenience, impacting environmental sustainability, public health, and economic vitality. Conventional solutions fall short in addressing the dynamic nature of traffic, necessitating advanced approaches. Accurate traffic flow prediction stands as a pivotal solution. It empowers proactive management, aids in reducing congestion, and forms a cornerstone for sustainable urban mobility solutions. Traffic or traditional traffic predictions grapple with inherent limitations. They often rely on rigid structural expressions and assumptions, proving inadequate in capturing the intricate variability of traffic data. Deep learning has emerged as a transformative paradigm in traffic prediction. Its data-driven approach and capacity to discern complex patterns have revolutionized the accuracy and scope of traffic flow forecasting. In order to analyze pre-processed data and evaluate the effectiveness of traffic flow prediction models, the neural network-based model on the GRU architecture was employed for model training and evaluation. In this research, we aim to predict traffic flow at four different junctions using a GRU neural network model. Gated recurrent unit is a variant of recurrent neural networks. Its adaptive gating mechanism enables a better retention of long-term dependencies, making it an ideal choice for modeling complex temporal sequences in traffic data. The GRU architecture consists of the following components. We have the input layers, the hidden layer, the reset gate, the updated gate, the candidate activation vector, and finally the output layer. For the input layer, it takes a sequential data, such as a sequence of words or a time series of values, and feeds it into the GRU. The hidden layers is where the recurrent computation occurs. At each time step, the hidden state is updated based on the current input and the previous hidden states. The hidden state is a vector of numbers that represents the network's memory of the previous input. For the reset gate, which determines how much of the previous hidden state to forget, it takes as input the previous hidden state and current input and produces a vector of numbers between 0 and 1 that controls the degree to which the previous hidden state is reset at the current time step. For the update gate determines how much of the candidate activation vector to incorporate into the new hidden state. It takes as input the previous hidden state and the current input and produces a vector of numbers between 0 and 1 that controls the degree to which the candidate activation vector is incorporated into the new hidden state. The candidate activation vector is a modified version of the previous hidden state that is reset by the reset gate and combined with the current input. It is computed using the hyperbolic tangent activation function that squashes it into output between -1 and 1. And finally, the output layer takes the final hidden state as input and produces the network's output. This could be a single number, a sequence of numbers, or a probability distribution over classes, of course depending on the task at hand. Beginning our analysis with exploratory data analysis is consistently a wise decision as it helps us understand important dataset properties such as time format, number of samples, and data types. In this case, the dataset we were working with contains more than 48,000 data points with 4 attributes. We should note that there is just a limited availability of public transportation data, which causes a limitation in our research. The model incorporates 4 GRU layers, each with varying numbers of units to capture hierarchical features of traffic patterns. The first layer 150 units, same for the second layer, and the third and fourth layer with 50 units. All GRU layers utilize the hyperbolic tangent activation function and are configured to return sequences as they are stacked to allow the comprehensive traffic pattern analysis. To mitigate overfitting and enhance generalization, a dropout layer with a dropout rate of 0.2 is added after each GRU layer. Dropout randomly omits a fraction of input units during training, contributing to a more robust and reliable model. The model concludes with a dense layer comprising a single unit. This architecture aligns with the regression nature of the task, where the goal is to predict a continuous value representing traffic flow. The model is compiled using stochastic gradient descent as the optimizer. This optimizer is augmented with a small weight decay and a momentum of 0.9 to enhance training stability. Also, the mean square error is employed as the loss function during training, which is a suitable choice for regression problems. The model undergoes training for 50 epochs, with the training data partitioned into batches of size 150. Early stopping is implemented as a callback, monitoring the validation loss. So the training halts if the validation loss does not improve by at least 0.001 for 10 consecutive epochs. The model with the best validation loss is restored, ensuring optimal prediction performance. To validate the proposed methodology, we conduct a series of extensive experiments. These experiments utilize our robust dataset containing historical traffic information. The experiments aim to demonstrate the model's efficacy and its ability to make accurate traffic flow predictions. The transformed training dataset for all 4 junctions were meticulously tailored to align with the specific requirements of the corresponding model, as illustrated in these figures. Each junction, distinct characteristic, and data intricacies were taken into account during the model fitting process ensuring a precise alignment between the data and predictive models. This meticulous approach to model data integration serves, served as a foundational element in our endeavor to develop accurate and context-aware traffic flow prediction models for urban intersections. The assessment of our traffic flow prediction model has yielded insightful performance metrics, specifically for Junction 1. The model has demonstrated robust predictive capabilities characterized by an RSME of 0.24. The same goes for the second and third junction. However, for the fourth junction, which presented inherent challenges due to the limited data availability, has registered a comparatively elevated RSME of a value of 1.024. Nevertheless, it is worth noting that the model has consistently displayed a noteworthy level of performance across all four junctions, emphasizing its ability to furnish valuable traffic flow predictions. In order to ensure that our predictive outputs remain consistent with the original data scale, we meticulously reversed the transformations that had been initially employed to mitigate the impact of seasonality and trends within the datasets. This pivotal undertaking serves to realign our predictions with the authentic traffic flow values, thereby bolstering the practical utility and interpretability of our predictive models. Sorry. Upon reverting the data transformations, a salient observation comes to the fore. Our predictive accuracy experienced a substantial enhancement. This pivotal step not only reverts our forecasts to the original data scale, but also underscores the precision and reliability intrinsic to our predictive models. The research findings carry substantial implications for urban traffic management. The accurate multi-intersection predictions empower city planners and policymakers with actionable insights, enabling informed decisions to alleviate congestion and traffic and enhance traffic efficiency. The implications extend beyond theoretical advancement, translating directly into real-world applications. Implementing the developed model in intelligent transportation system can revolutionize traffic signal timing, road expansions, and overall infrastructure planning, fostering more sustainable and efficient urban mobility. The research culminates in the development of a robust multi-intersection traffic flow prediction model, leveraging deep learning techniques, particularly the GRU architecture. This model significantly enhances accuracy and aids in proactive traffic management, aligning with the broader goal of energy-efficient urban mobility. Future research aims to expand the model's capabilities, potentially incorporating real-time data streams and adaptive learning mechanisms. Additionally, exploring its applicability in dynamic traffic scenarios and scalability to larger urban networks remains a promising avenue for further research. And thank you.